Hello class. Today we're going to be learning about cycloalkanes, alkenes, and alkynes. Cycloalkanes, as their name suggests, are alkanes that are cyclic in nature. Now, this is a huge reason why we have such a great variety of organic compounds. A lot of complex compounds in your body, in the foods we eat, they incorporate these ring structures. Now, when we're naming these structures, we have to include the prefix cyclo. So let's say we had an unsubstituted ring of a hydrocarbon ring, and it contained 6 carbons. We would call that cyclohexane, right? We take still hexane, that parent chain name, a 6-carbon alkane, and we add the cyclo prefix. What if we had one that had, say, 5 carbons? What would we call that? Yeah, that'd be cyclopentane. So cyclic hydrocarbons must have the cyclo prefix. Now, what happens if your ring has substitutions, has alkyl groups? Well, we're going to add a couple caveats to your existing naming rules. Now, your existing naming rules you will still utilize here, but there's 2 big caveats. Number 1, the ring is considered to be the parent chain. So always list that ring structure, your ring cyclic hydrocarbon, as the parent chain. And number 2, the carbons are numbered such that substituent groups have the lowest possible numbers. Now, this can be a little tricky for students because on a ring, is there a start and an end point? Well, I hope you just said no to that question. There is no start and end point, right? You can start with any carbon in order to label your ring. Here we have 2 examples. Let's tackle this one first. What is our parent chain? It's going to be our ring, right? So how many carbons are there in our ring? There's 1, 2, 3, 4, 5, 6 carbons. So we know that our parent chain is what? It is cyclohexane, right? 6 carbon, cyclic ring, all single carbon bonds. It is cyclohexane. Now we need to figure out how we're going to number this thing. Keep in mind, we do want to give our substituent groups the lowest numbers possible. And we can start by labeling anywhere on our ring. It so happens that in this case, the way to number this would be 1, 2, 3, and 4. Now, if you numbered it any other way, you will notice that the numbers add up to a greater value than 1 plus 2 plus 4, which is 7. Right? If you numbered it this way, it would be 1, 2, 3, 4, 5, 6. Right? They have much higher numbers than if you label it this way. So where are our substituent groups? Well, we have substituent groups at 1, 2, and 4, and these are all methyl groups. So this is 1, 2, 4 trimethyl. Right, we combine that together. This compound is 1, 2, 4 trimethyl cyclohexane. And yes, you do write that all as one word. Okay, now let's look at this example here. You're going to notice by numbering it, there's 2 ways that you could actually correctly number this thing. But there is an obscure rule which will tell you how to number it. So we could have done it like this. You could go 1, 2, 3, 4, 5, 6. Or you could go 1, 2, 3, 4, 5, and 6. You'll notice that either way, you have substituent groups at 1, 3, and 6. So in a situation like this, what is the correct way to label it? So in this situation, believe it or not, the red numbering here is correct. We default to alphabetical order. So if there is ever contestation between two different labels, you must use the alphabetical order to determine. So apply the lowest numbers possible to those substituent groups in alphabetical order. Because ethyl comes before methyl, the red numbers here are correct because that gives it carbon 1. So again, let's list our parent chain. Our parent chain here is cyclooctane, and we have substituent groups at 1, 3, and 6. So we have 1 ethyl, we have 3 methyl, and we have 6 methyl as well. Now if we add this all together and create our name, we get 1, 3, we have 1 ethyl, we have 3, 6 dimethyl.
Excuse the interruption, Ms. Thorne to the front door, please. Ms. Thorne to the front.
Cyclooctane. Alkenes are hydrocarbons that have at least one double bond within your molecule. Now, these alkenes will now make them unsaturated hydrocarbons. Right? You add a double bond, your hydrocarbon is no longer fully saturated with hydrogens. Now, when we name these, we give it the suffix "ene." Right? With alkanes, we use the suffix "ane." With alkenes, we use the suffix "ene." So if it was propane, and we add a double bond, that would now be what? Propene. Alkenes take the general formula CnH2n plus 2 minus 2x. Don't stress too much about the general formula, but note that your double bond, how many less hydrogens do you have now? Well, you have 2 less hydrogens, right? What's taking that place is now another covalent bond between your 2 carbon atoms. Right? X here represents the number of double bonds. So if we look at ethene and 2-butene, let's figure out their molecular formulas and their structural formulas. So what is the molecular formula for ethene? Well, what does eth stand for? Well, that's 2 carbons. And if it was an alkane, that would be C2H6. But since we've removed 2 of those hydrogens by adding a double bond, our molecular formula is now C2H4. And what does our structure look like? Well, that's going to be C double bond C, H, 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 H. Remember, you still want to ensure that all of your carbons have 4 bonds, but this bond is making it unsaturated. Right? We're removing 2 hydrogens. There's less than the maximum number of hydrogens possible. What about 2-butene? Again, if it was butane, that's 4 carbons. So that would be C4H10. So we are now removing 2 hydrogens by adding a double bond. So that is C4H8. And if we were to draw the structure for this, we have a double bond at carbon 2. That's what this 2 represents. So I'm going to get a little lazier on this one here. I'm going to do condensed structural. And these carbons here each have 3 bonds. So, you know what, I'm just going to draw the hydrogens in like this. So they each have an additional hydrogen that we must add in order to have 4 bonds for carbon. Lastly, today we are going to explore alkynes. Now, alkynes have 1 or more triple bonds within the compound, within the molecule. So if you see a triple bond, you must use that suffix "-ine", Y-N-E. Now, these take the general formula CnH2n plus 2 minus 4x, where x represents the number of triple bonds. Again, don't focus too much on that. Just know for each triple bond, how many hydrogens are you removing? Think about it. Now, instead of having just 1 carbon-carbon single bond, we have 1, 2, 3 covalent bonds. Each of those bonds is going to remove 2 hydrogens. So in total, in alkyne, you're removing 4 hydrogens for each of your triple bonds. Again, let's explore the molecular formula as well as the structural formula for these 2 molecules. So for ethine, again, every time we add a triple bond, we are actually removing 4 hydrogens. So ethane would be C2H6. If we remove 4, the molecular formula for ethine is C2H2. Now, what would be the structural formula for this? Well, that's C, triple bond C. And remember, each carbon needs 4 bonds, so we are adding additional hydrogens on each carbon here. To butane, again, butane would have the molecular formula C4H10. And with that triple bond, we are removing 4 hydrogens. So that's going to be C4H6. And we find it looks something like this right here. And again, just like alkenes, this number in front here tells us the position of your double or triple bond, right? In this case, the triple bond. So when it comes to naming alkenes or alkynes, there are some additional rules now that we have to add. So first one, your parent chain must contain the double or triple bond even if it is not your longest chain. I'll show you a couple examples where that's the case. So there is an exception to that rule we learned earlier, right? If it's not your longest chain, that's okay. It has to contain that double or triple bond. Of course, you want to have the longest chain that does include your double and triple bond, however. Number 2, the position of the double and or triple bond determines how the parent chain is numbered. You want to give your double or triple bond the lowest number possible. So it's kind of nice in the sense when you're working with alkenes and alkynes, you don't got to think about which substituent group, which substituent group where would give you the lowest numbers possible. You always give the lowest number to your alkene or alkyne, to that double or triple bond. And number 3, if there's more than 1 double or triple bond, you must use prefixes just like you did with methyl and ethyl and things like that. So instead of it being, for example, let's say there's 2 double bonds in your butane molecule. So you add 2 double bonds. We add them at 1 and 3. So I would say that would be 1,3-butadiene. So you do add that di right before your suffix -ene. So let's do this example together. First up, we need to figure out what is our parent chain, right? The same rules still apply. You always got to find your parent chain first. So, what is our longest chain here that includes our double bond? This is where you need to be a little bit careful. Because if we were looking just for our longest chain, it would be 1, 2, 3, 4, 5, 6, 7. Or you could say 1, 2, 3, 4, 5, 6, 7. But that would not include your double bond. So in order to include our double bond, our chain must be this here. Or you could incorporate this here. It doesn't really matter which way you do it, right? It'd be the same either way. But that must be our parent chain so we can incorporate our double bond. So the next question is, well, how do we number this monstrosity? How do we number this? Remember, we don't need to think here about our substituent groups. We just number it such that our double bond gets the lowest number possible, which in this case would be 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And now we have substituent groups here at 5 and here at 2. So what is our parent chain in this case? Well, our parent chain now is going to be how many carbons? 1, 2, 3, 4, 5, 6. So this is going to be 1 hexene, right? The 1 to represent where that double bond is in our parent chain. And we're changing that suffix to -ene now instead of -ane. Now what about our substituent groups? Well, we have one here at carbon 2, which is in ethyl group. And we have one here at carbon 5, which is a methyl group. And if we combine this all together, we get a final name of 2-ethyl 5-methyl 1-hexene. Now, this may look confusing to you, but as long as you follow those rules to a T, you will get the right answer. You can see, though, that as we add more rules, these names get longer and longer and longer. So let's do one more example to illustrate alkynes. So here we have a molecule with 2 triple bonds. First things first, let's identify our parent chain. What is our parent chain? Well, it's going to have to incorporate all of our triple bonds and be the longest chain that does so. So that is this right here is our parent chain. Now the question becomes, how do I number this? You may be tempted to do this. 1, 2, 3, 4, 5, 6, 7, and 8. But you'd be wrong. Why would you be wrong? Think about it. Why would you be wrong here? Well, if I label it the other way, right, if I do 1, 2, 3, 4, 5, 6, 7, and 8, where are my triple bonds? Because remember, that's what matters. We want to give our double or triple bonds the lowest numbers possible. Here, my triple bonds, if I look at the blue numbers, I have 1 at 2 and 1 at 5. If we look at the red numbers, I have 1 at 3 and 1 at 6. So the blue numbers here give me a lower total value. So we would label it from right to left in this case. So what is our parent chain here? Our parent chain will be 2, 5, what? 2, 5 what? So we have 2, 5, octa, and then we must use the prefix di because we have 2 triple bonds. And then what is it? Well, it's triple bonds, so we use the suffix "-ine". So it's 2,5-octadiene. Wow, does that ever sound awkward? 2,5-octadiene. And our substituent group here, we only have one, is on carbon 5, and that is 5. Oh, sorry, it's on carbon 4, and that is going to be 4 ethyl. 4-ethyl. So when we combine this all together, we find that the name of our molecule is 4-ethyl 2,5-octadiene. Alright, so that is all for today. If you have any questions at all, let me know. Have a wonderful day, everyone.